Hello everybody, this is Dr. Christopher White and welcome back for part 2 of the Precambrian its life history, focusing on the Proterozoic. So at the end of the previous presentation we'd been discussing Wilson cycles. So the question is, well, why are we suddenly interested in Wilson cycles? Well, it just so happens that the Proterozoic rocks are the first time that we can begin to see indications of these Wilson cycles having occurred. So around 1.94 billion years ago, a basin began to open up on the northwestern coast of Laurentia. The basin was enclosed around 1.84 billion years ago, so the basin formation and its closure took somewhere in the region of about 100 million years. So the closure of this basin ended up producing what's referred to as the Magmatic orogeny. Now, part of the Magmatic sequence consists of a suite of sedimentary rocks called a sandstone shale carbonate assemblage. Now, we know this assemblage because this is the standard sequence of rocks you get off a passive continental margin. So if you remember, the sandstones represent the beach environment going into the shallow marine environment. Then as we go into steadily deeper water, we lose the sands and they're replaced by muds. And then if conditions are correct, the muddy sediments give way to carbonate-rich sediments. And so we end up with a sequence of sandstone, shales and carbonates. And this sequence is a passive continental margin sequence. So not only does the Magmatic orogeny show us that one of these Wilson cycles is taking place, it also gives us good strong evidence for the presence of a passive continental margin, which, if you remember, is something we didn't have in the Archean. And just to follow up on the point I made earlier, passive continental margins are where life likes to be. It's nice, it's safe, it's boring. So we also find the same sequences of rocks occurring in the Pinocchian orogeny. So this is on the south coast of Laurentia. During the Pinocchian orogeny, we see this same sequence of rocks appearing, which also suggests that the south coast of Laurentia was also a passive continental margin. So this is the basic model for the Magmatic orogeny. So just to give you some idea, the Magmatic orogeny itself is this dark orange region here. Then either side of it we have an arc, a volcanic arc here, and a volcanic arc here. So in terms of the Magmatic orogeny itself, this area represents the northwest of Laurentia, and just like with any Wilson cycle, the area began to be uplifted, it began to be extended, and we ended up forming a rift valley. So the formation of the rift valley eventually led to crustal thinning, which allowed the mantle underneath to melt through decompression. That produced the mafic magma. The mafic magma pushed its way through the crust, obviously forcing these two plates apart and allowing the formation of oceanic crust. So obviously this piece of continental crust goes off to the west, this piece is pushed to the east, and we end up forming an ocean basin in between. Now the ocean basin kept getting larger and larger and larger, and during this time period on both shores of this sea that opened up, we had passive continental margins. So this is where we're going to get our sandstone, mudstone, carbonate sequence being deposited. So we're going to find it on this side over here, and we're going to find it on this side over here. Now eventually a subduction zone opened up, we believe on the western margin of the ocean basin, and this obviously led to the oceanic crust subducting down into the mantle and being destroyed. This obviously meant the two pieces of continental crust would move towards each other. Obviously, as part of this process, as the oceanic crust was subducting down, the sediment on top of the oceanic crust got scraped off, so it started to build up right here in the trench area. And steadily over time, as they got closer and closer together, eventually we had a continental collision, and this produced our orogenic belt, so essentially our mountain range. And as part of that mountain range, we have these sandstone, mudstone, carbonate sediments which were being deposited along the margin of the ocean basin. So if we look over here, we can see the Magmatic orogeny itself in this deep purple. This represents this area here. Okay, so it represents the continental crust and the sediments from within the basin that have been deformed as part of the mountain building process. And then we have this lighter orange area here. This represents the island arc, well, should I say the continental arc that went and formed due to the subduction and the magma that it went and produced. So this essentially is our line of volcanoes that were formed as part of the subduction process. And so what we can see with the Want-May orogeny is we can see this is the first time we have a nice complete Wilson cycle visible in the rock record. This is very important because it obviously tells us by this point plate tectonics is functioning normally. So let's keep going. So we formed our continental core for Laurentia by about 1.84 billion years ago. So during this time, Laurentia began to accrete new island arcs and crust along its eastern, southeastern and southern margins. So along the east coast, the southeastern coast and the south coast is where Laurentia is going to do most of its growing. There were several key orogenies, and each of these orogenies was followed by a period of plutonism. So plutonism just means abundant intrusive events. So lots and lots of intrusions were placed into the crust during these post-orogenic periods. So there are several key events that help to increase the size of Laurentia. And these are the Yavapai orogeny, that's 1.76 to 1.72 billion years ago. The Mazatzel-Labradorian orogeny, that's 1.69 to 1.65 billion years ago. The formation of the Granite-rhyolite province, that's 1.55 to 1.35 billion years ago. And finally, the Grenville orogeny, that's 1.3 to 1 billion years ago. And each of these events is going to help to add mass along the margins of Laurentia. So the Grenville orogeny is important because it marks the formation of Rodinia, so one of the supercontinents that was present during the Proterozoic. So the early stages of the formation of Rodinia began about 1.35 billion years ago, so about the end of the Granite-rhyolite province, and Rodinia eventually broke up at about 0.78 billion years ago, so towards, right towards the end of the Proterozoic. So the rifting that led to the breakup of Panatea also led to the formation of an ocean basin which is called the Iapetus Ocean, and you're going to have to remember that name because it's going to turn up quite a bit when we discuss Paleozoic geology. So the Yavapai and the Mazatzel-Labradorian orogenies were the result of the accretion of juvenile crust. So juvenile crust, as the name suggests, simply means new crust. And it's mostly made at spreading ridges, but it also consists of any sediments deposited on top of the oceanic crust. So what we're seeing essentially is just, if we go back to the Want-May model here, so all of this material in the basin here is going to be considered juvenile material, it's new material. And so what we see is, as part of the orogeny itself here, we have this area marked in yellow. So this is going to be a mixture of sediments from the ocean basin and also with a few bits of the oceanic crust as well mixed in there. And so this is going to be our juvenile material. And so what we're going to see is, as part of these events that are going to take place to help to add mass to Laurentia, we're going to see juvenile material piling up along the east, southeastern and southern coasts of Laurentia. So in terms of the Yavapai and the Mazatzel-Labradorian orogeny, they are both Wilson cycles, so we've had a basin open and a basin close, and that results in an orogeny. And obviously, as part of the mountain building process, we also get a large amount of intrusive events taking place, so we see lots and lots of intrusions. The Grenville orogeny is a continent-continent collision, so it's not exactly the same as the others. So in the case of the Grenville orogeny, we have two very large pieces of continental crust essentially hitting each other, as opposed to Wilson cycle, which is more of a smaller, more localized event, depending on how you classify it. So in terms of the Yavapai orogeny, you can see it's marked out here in green. So this is the area that's been affected by the orogeny. And you can also see we have these dark green colours here. These represent areas where we have had granitoids being intruded. So essentially these represent felsic to intermediate intrusives associated with the orogenic event. So what's happened here is, along the south coast, we've had a basin open up. So we've had new oceanic crust being formed. Obviously, we've had sediment deposited on top of that new crust, and then we've had subduction and the closure of the basin, resulting in convergent tectonism. So we've had essentially a collision between two pieces of continental crust, and it's ended up forming this Yavapai province here, which represents an orogenic belt. So it's a area of elevated terrain associated with the collision of the pieces of continental crust. You can see marked on the diagram here. We have this line here, so this is representing a subduction zone. So what's happening is we're having the oceanic crust being formed, is being subducted along the southern margin, and that means essentially as the oceanic crust gets subducted, the continental crust and any island arcs associated with it are going to be essentially compressing the material within the basin. As the basin gets smaller and smaller and smaller, the material gets more and more compressed, and it ends up forming our mountain range, our orogenic event. So obviously as part of this mountain range forming process, we end up forming quite large quantities of felsic and intermediate magmas, both due to subduction and also due to thickening of the crust during the actual collision itself, and this leads to the formation of quite large quantities of felsic and intermediate magmas which intrude the crust, forming rocks like granite and diorite. So the Yavapai orogeny was followed by the Laurentian orogeny. You can see it's marked out in blue on this diagram, and it's essentially exactly the same thing. So we have an ocean basin open up, we have a new ocean basin form, fill with sediment, and then we have the destruction of that ocean basin, and obviously we produce a mountain range as a result of that. Once again, just like the Yavapai orogeny, we have in darker blue here, we have several large bodies of felsic and intermediate magma which are being intruded as part of that event. So both the Yavapai and the Labradorian orogenies, they are relatively straightforward and easy to understand. They are essentially just operating on exactly the same principle as the Wampme orogeny that we discussed a few slides earlier. Now, when it comes to the Granite-rhyolite province, on the other hand, things get a little bit more interesting. So you can see the Granite-rhyolite province is a very, very large area, marked here by this kind of slightly brownish green colour. But you can also see it has lots and lots of associated intrusives. So we have lots of this mint green material here, and these are the felsic and intermediate magmas that are emplaced along, at the same time as the Granite-rhyolite province is forming. Now, in the case of the Granite-rhyolite province, the mechanism that ends up forming it actually differs from the Yavapai and the Labradorian orogenies, and we're going to discuss the Granite-rhyolite province in greater detail in just a second. And then after the Granite-rhyolite province, we then have the addition of the Grenville orogeny that helped to add continental crust in here and down here. And you can see we have several small pieces, and this is the result of as I said, a very, very large supercontinent forming event. This is going to end up leading to the formation of the supercontinent Rodinia. Okay, so in terms of the Mesoproterozoic accretion, so if you remember, Mesoproterozoic means middle Proterozoic. So while the other orogenies accreted material onto Laurentia's south and eastern margins are relatively simple to explain, the Mesoproterozoic Granite-rhyolite province is a little less straightforward. So we think the Granite-rhyolite province might represent an incomplete Wilson cycle. So we've started to form our ocean basin, or at least we've started to take the steps to form it, but we never actually managed to make it all the way to a proper ocean basin. So the Granite-rhyolite province likely represents a continental rift environment, so like the East African Rift Valley. So this is an area where our continental lithosphere is being extended and thinned, resulting in the formation of a rift valley. And we are a little uncertain as to why the rift valley formed. So the exact mechanism that's causing the crust to be extended is uncertain, although we think it might be due to back arc extension. So if we just go back a second, we think there is a chance we might have had a subduction zone running down here along the eastern side. This would have meant that we had essentially an island arc or a continental arc forming along here. And if you remember, when we were discussing the idea of slab rollback, that means behind these arcs we can get the formation of, well, we can get the extension of regions of crust located behind the arc. And this, of course, is called back arc extension. And so that could be a possible explanation as to why the Granite-rhyolite province forms. It might be due to a subduction zone, slab rollback extending the continental crust and making it start to rift. So crustal thinning would of course have led to the formation of mafic magmas due to mantle melting. So let's just go all the way back to our Want-May diagram. Here we go. So we think the situation is our piece of continental crust is starting to be extended. So one half obviously wants to go one way, one half wants to go the other way, and this region in the middle here begins to undergo extension. So that's our rift valley. Obviously the mantle underneath starts to melt because the overburden gets reduced, so it's under less pressure. And this is obviously going to lead to the formation of large quantities of mafic magma through mantle melting. Now, the granites that we see in this area are what are classified as A-type granites. And these A-type granites typically form due to crustal melting associated with mid-continental rifting. So this is why we believe that the Granite-rhyolite province represents the essentially a rifting region of continental crust. So in terms of the melting of the continental crust to make these granites, it was probably driven by heat from the mantle-derived mafic magma. So if you remember, when we melt a mantle rock, so of course which is ultramafic, we end up forming a mafic magma. So the mafic magma is going to be quite high temperature, so it could be anywhere between about 1200 to 1400 Celsius in temperature. Whereas your average piece of continental crust, if it's wet, will start to melt at quite low temperatures, down in the 650 to 700 Celsius range. So assuming you have, a wet continental crust, so there's some water around, and you obviously have the heat from these very, very hot mafic magmas, that's going to be sufficient to induce melting of the continental crust, and that's obviously going to lead to the formation of these A-type granites. So the melted continental crust would obviously have a felsic composition. That obviously leads to the emplacement of the granites, but it will also lead to the eruption of felsic lavas into the rift valley. And obviously the most common type of felsic lava, or most common type of rock, formed by felsic lavas will be rhyolites. So once again, we're going to go back to our Want-May model. So here we go. So we've got our mafic magmas forming down here. They're going to be heating up the base of the continental crust, causing it to melt. That's going to produce felsic and intermediate magmas. So some of the magma will make its way to the surface where it will be erupted, and that will form rocks like rhyolite and also lesser andesites. Whilst the vast majority of the magma formed will never make it to the surface, so it will get stuck in the continental crust where it will cool down and crystallize to give us rocks like granite and diorite. And so what we have is a situation where we have a region that's being intruded by all these granites and and lesser diorites, and we have the eruption of felsic lavas and intermediate lavas onto the surface, giving us rhyolites and lesser andesites respectively. So we also have some mafic intrusions and basaltic lava flows, and these represent the mafic magma that's being produced through mantle melting. So some of the mafic magma that's produced by mantle melting will make its way into the crust, where it will get stuck and it will crystallize to give us plutonic mafic igneous rocks like gabbro. We will also see that some of the mafic magma will make its way all the way to the surface where it will be erupted, and obviously that mafic lava will cool down to give us basalts. And so what we see in the Granite-rhyolite province is we have a region which appears to have undergone extension. That appears to have led to mantle melting, which in turn has then melted the continental crust to some degree, producing large quantities of felsic and intermediate magmas. Most of this magma gets stuck in the crust where it crystallizes granites. Some of it makes it to the surface where it's erupted by volcanoes and it forms the rock rhyolite. And then on top of that, we also have the emplacement of some mafic plutonic igneous rocks and some mafic volcanic rocks due to the movement of some of this mafic magma through the crust. So you can see that what we have here is a reasonable explanation as to what we're seeing. So the rift itself would also have filled with clastic sediments, because obviously there's going to be high ground on either side of the rift. That high ground is naturally going to have a relatively high rate of erosion, and so that means we're going to have lots of clastic sediments being deposited into our rift valley, along with the rhyolites and the occasional andesite or basalt flow. So we can see these clastic sediments because they are currently present as silica-rich metamorphic rocks, primarily quartzites. Although some of these quartzites may also be due to the metamorphism of rhyolite layers, because rhyolite is also a very silica-rich rock, which, if metamorphosed, could also end up forming a quartzite. But either way, we have evidence for a rift valley system that's filled with lots and lots of rhyolite flows, a few basalt flows, a few andesite flows, and a mixture of clastic sediments. Kind of pretty much what you would expect to get in your average continental rift valley. Now, the reason we consider the Granite-rhyolite province to be a failed Wilson cycle is because it never actually made it to the point where we started forming large quantities of oceanic crust. So an ocean basin never actually opened up. It started, but it never went all the way to the point where we actually started forming a body of water between our two pieces of continental crust. So the Granite-rhyolite province is best thought of what's referred to as a large igneous province. And this is a region of extended volcanic activity, and a classic example would be somewhere like the Deccan Traps of India, where you had huge basalt eruptions going on for tens of millions of years, particularly during the Cretaceous. So following the Granite-rhyolite province, we then had the Grenville orogeny. So the Grenville orogeny is also a Mesoproterozoic event, and it occurs between 1.3 and 1 billion years ago. Now, unlike the earlier Yavapai and Mosatzel-Labradorian orogenies, the Grenville orogeny is due to a much larger continent-continent collision. So in the case of the Yavapai and the Mosatzel-Labradorian orogenies, what we had was Laurentia rifting, creating a small ocean basin which then went enclosed, producing a mountain range. In the case of the Grenville orogeny, we actually have two much larger pieces of continental crust colliding with each other. So think of it like North America colliding with Europe. So what this means is obviously there has to be an ocean basin in between them that gets destroyed, and obviously we have these two very large pieces of continental crust smashing into each other. So it is a Wilson cycle, but on a very large scale. So the oceanic crust between the continental land masses subducted in a northwesterly direction, if we are thinking about North America in its current orientation. So the oceanic crust subducted northwestwards under Laurentia, and this meant that the eastern, southeastern and southern margins of Laurentia formed a volcanically active mountain chain. So for a modern example of that, think of the Andes. So a nice big mountain range full of volcanoes, lots of earthquake activity. And of course that's, in the case of the Andes, it's due to the subduction of the Nazca plate underneath the South American plate. So eventually the ocean basin between the two continental land masses would be destroyed, and you would eventually get the collision of the pieces of continental crust, and this obviously is then going to lead to the formation of a mountain range. So in terms of the most southerly extent of this collision with regard to Laurentia, the last piece that we see is located in Llano province in Texas, whereas the northeasterly limit is located in Newfoundland in Canada. So it's quite an extensive mountain range that went and formed. So it would have been cutting all the way from Newfoundland in Canada all the way down to central Texas. Now, in terms of what pieces of continental crust are actually colliding, it's a little bit difficult to know exactly which one is impacting. So when it comes to the collision that we have along the eastern seaboard of Laurentia, so this area along here, we think that it's related to either the Amazonia craton making contact, or the Rio de la Plata craton making contact, or both of them making contact. We're not honestly 100% sure. Now, both of these cratons are actually nowadays part of South America, But at the time they were moving on their own, and we think that one or both of them made contact with the eastern coast of Laurentia. Now, in terms of the Grenville material that we see down here along the southern margin of Laurentia, that's even more difficult to try and work out what produced that. We think it may have been the Kalahari Craton, which is now part of Africa, making contact with the south coast of Laurentia, but once again we're not 100% sure. There is the possibility it could have been the Congo Craton, but the Kalahari seems like a more reasonable choice. So although we're not 100% certain exactly which piece of continental crust was actually doing the impacting, we do know it was a rather large continent-continent collision. So these collisions that produced the Grenville orogeny, marked the final stages of accretion of Laurentia and the formation of North America's Precambrian basement. So by this point, around 75% of the North American landmass, of course, which at the time was called Laurentia, was now present, with the additional 25% primarily accreted along the western and southern margins of Laurentia during the Phanerozoic. So this is our basic situation. Obviously we have the Grenville orogeny here and here. It would have actually formed a continuous chain that came all the way down here, but these are the areas where we actually have exposed material related to the Grenville orogeny. And as discussed, it's either the Amazonia or the Rio de la Plata cratons which appear to be making contact with the eastern coast, whereas on the southern coast here we think it's probably the Kalahari craton, which is leading to the continent-continent collision down here. So around 1.1 billion years ago, we had the start of tensional forces in the center of Laurentia. So tension means extension, so the crust is being stretched. So this starts in the final 100 million years of the Grenville orogeny. So the Grenville orogeny is still taking place whilst this extension begins. If we look at the location of this extension, you will see that it's located here to the rear of the Grenville orogeny. So the Grenville orogeny is coming down like so. And this area here is the region which appears to undergo extension. Now the reason for this extension is uncertain. It may be some kind of back arc situation where we have slab rollback at the subduction zone here, which causes the crust in this area to begin to move eastwards and causes this area behind to begin to be stretched and thinned out. But we're not 100% sure about that. So the rift itself forms a rather distinct U-shape. So we can see it here in this simplified diagram from the textbook. You can see the western limb here, the eastern limb here, and obviously a portion of it's hidden under Lake Superior right there. And you can also see it on the more detailed map here as this purple line coming round like so. So the western limb of the rift extends through Minnesota, Iowa, and Kansas, and the eastern limb extends through Michigan and Ohio. So the rift system failed after about 20 million years. So it did have, quite a good go at actually becoming a successful rift, but it didn't quite make it. So if the rift itself had continued, and it would have extended, and eventually it would have split Laurentia into two land masses. The first landmass would have consisted of the northeastern, northern, and western states of the US and Canada. And a second landmass would have formed that would have consisted of the modern-day southern US states, but it never happened. So why the rift opened up, we're not 100% sure. It's probably extension related to the Pinocchian orogeny. I do apologise, the Grenville orogeny, my mistake. But why the rift failed, uncertain. Okay, so this is a good time to stop part 2. So once again, stop the video, get up, have a walk around, get a drink of water, take 5 or 10 minutes to relax, and then please come back for part 3.